In this talk, in some sense, we continue the line of triangles, which was started today by Zoltan very recently. I mean, in one of the previous talks, we already discussed some triangles. Now we're supposed to discuss another famous problem concerning triangles. And the speaker is a very young person, Dmitry Zakharov, who will speak about acute sets.
First of all, call point set Rn acute set if x determine only acute angles. And the f of n is the maximal size of acute set in Rn. Small point set. Small acute set. This quantity was introduced by Dancer and Grunbaum.
When is the set acute?
Sorry?
You looked acute and you didn't say when it was acute.
Sorry.
When is it? You don't
It was set, but
X is acute if every 3 points in X determine acute triangle.
Every angle is acute.
Yes. This quantity was introduced by Dancer and Grunbaum in 1972. 60. And they conjectured that f of n equals to n minus 1. But then in 1983, Erdős and Furedi disproved this conjecture and showed using probability that f of n is larger than 1/2 to 1/8 up to nth power. Their approach was improved in 2011 by Victor Harangi. And he showed that f of n is greater than some constant multiplied over 1/21 up to nth power. Now we will prove that f of n is greater than square root of 2 power to n. This term easily follows from the recurrent inequality of which f of n plus 2 is at last 2 f of n. Let's prove this inequality. We take a maximal acute set in Rn, which such that size of x is f of n and x is acute. And for each point of x, first of all we fix some small value, small positive number r, and for each point x from x, we match two geometrical opposite points on a circle of radius r. We take two points of such kind. And now we consider a new set in Rn plus 2 y equals to a set of pairs clearly its size is double to f of n. We need to check that this set is acute. Let's take three arbitrary points of int with y. That would be x a, y b, z c. There x, y, and z from x, and a, b, c lies on the circle radius r. We need to check that the following formula is positive. X minus scalar product x minus z plus a minus b to a minus c. If this sum of scalar products is positive, then the angle y, x, z is acute. We have two cases. In first case, we have x not equivalent to y and x not equivalent to z. Y and z may coincide, may be the same. In this case,
I'm sorry, have you defined phi z, phi x? Have you defined it? What?
phi x is a point on a small circle. No,
Where is x is in your original set?
Yeah. And
x is a point of x first.
No, we are adding two dimensions, of course, but the next x is.
So to each point in x, we correspond to
Yes.
opposite point on the circle in an arbitrary way.
In an arbitrary way. That's what I missed. I missed the
Yes.
arbitrary way.
We need just that all these points are distinct.
Okay.
Okay. In this case, this part is positive and don't depends on r. But this doesn't exceed model of this thing doesn't exceed 4r squared, because length of this vector and length of this vector are at most 2r. So we can make this formula positive in this
At
case.
least minus 4r squared.
No, by modulo it's at most. In this case it's greater than 0. In the second case, we can suppose that x and y is the same, but then a and b will be the geometrical opposite points on the circle. In this case, this will be vanished, and this thing corresponds to such angle on the circle. Here A, B and C. C is different from A and B. But this angle is acute, so this quantity is greater than 0. So that this whole quantity greater than 0. So in the second case, angle is acute too. So in the all cases, angles is acute. Theorem is proved.
Amazing.
What we do? We have 10 more minutes for lunch, or we are discussing this
Maybe solve another problem.
beautiful result?
Ridiculously nice. The most embarrassing.
So, any questions? Any discussion? It's a very unexpected result.
Yeah. Ridiculous.
Okay?